Hello again, YouTube. This time I am going to take a huge leap from where I've been in previous videos. I'm entering my project, or trying to enter my project, into the Hackaday 2018 prize, so I'm going to try and leap up a level and explain the overall aim of this project that I'm on. The cinnamonBun here is it's intended to be open source hardware once I verified this by putting it into a target vehicle, which is where it's supposed to go into a 12 volt environment. Well, nominal 12 volt environment. So up to now my videos have been about this libsoup library of code, which is a low level library of code which basically removes the need for special function registers and messing with those special function registers to create timers, hardware timers, and we'll get on to other stuff, various communications and stuff. But this project is, on top of the libsoup, is a CAN node, which basically I've just added to my Git repository. So I've got to do readmes and license files, but this then enables, this manages this bundle of code. This project manages the CAN bus, these cinnamonBun's connection to the CAN bus. So just to go through, this is, as you can see, a piece of Cat5 which I've ripped to pieces for test purposes, and I've just got a test voltage coming in. Positive is in the center pin. This 5-pin connector, we've got the center pin is positive. The pin on either side are both ground, so positive in the center and then ground on each side, and then CAN high and CAN low are the two extremes. That means that you can actually switch this cable one way or the other and you won't upset the voltage, as long as the positive voltage is in the center pin. Now it will upset, you can't connect CAN high to the CAN low and vice versa. So in this color, blue is always on one side and the white and blue is always on the other side, so you want to keep that convention. Now this simple test CAN bus is terminated on either side with a 120 ohm resistor just twisted onto the data lines, the CAN high and CAN low. So that's our CAN bus for test, 3 cinnamonBun nodes, and all of them running this software with an application. Now the application is just simply made up of an initialization function, which is called on power up, and then the main app main is processing, which is added to the main loop of the CAN node management software. So as well as managing the nodes, all the CAN bus infrastructure, it will call your app main at regular intervals. So getting back to this, if I power this up just to show you what it's going to do, once the node has powered up and is happy that the CAN bus is functional, then it will call the initialization function. So you can see these 3 outputs light up. And what's happening here is this application on this input node is monitoring 4 switches, and if it detects a change, it's just sending out a frame onto the network. Now it's not sending a frame directly to this output board. It's sending out a status to say my switch status has changed. It's the master that takes an action accordingly. So the logic is built into this node. So if I now press a switch, the frame is still going out, but nothing's going to happen on the network because nothing is processing that and saying some action should be taken. So the master now, it's listening for a status update from this switch, and once it receives that status update, it sends out. Now you can send out whatever combination of data that you think is relevant for your network. So in this case, I've got a second node. Now this has got these two nodes have got an an IO address of 1. But one is input node 1, one's output node 1. This is output node 2. And this master, we'll look at the code here in a minute, but this master is just receiving this input and it's sending one frame with data for both of the connected. So it's sending out a single output frame saying output node 1 channel 0 is on or off. Node 2 channel 0 is on or off. And if I look at the code for the input application is probably the most complicated, because once it's called, the initialization function is called, it sets up a handler for the status request message, which I'll come to later. I shouldn't get into that because it's not really that relevant. Apart from setting up that handler, it creates a frame, fills out that frame given its current inputs. So the switches, it looks at the switches, what are they, and then sends a frame to the master, so the master knows what, or anybody in the network can see what the status of the frame is. So the main just monitors those switches, and if the switch changes its status, it does some software debouncing, but once it's happy that the status changed, it sends out a frame. It ultimately sends out a frame. Now the master on initialization, it tells the node underneath it, libesup and the ESCAN node, I'm interested in the input status. That frame identifier. When that frame identifier comes in, I want you to call this function. In a similar way, there's an analog input. So if ever there's an analog input frame on the network, I want you to call this function. And then the master's main does nothing. It just returns 0, which is success in my parlance. And that's all the master does, is it processes inputs, switch inputs and analog inputs. And the function for processing input, when each byte it receives will come from an IO node. It'll have a channel identifier for what channel the status is for, and then it will have an on or an off. The last bit is on or off. So that's all the master does. The master just sits here processing these, and it sends out, this handler handles input status messages, and it transmits output status messages. Now I've also got an analog handler which handles the input status, and it's going to send out, when it receives an analog input, it's actually going to send out a switch output status, and it's going to send a data byte to node 1, IO node 1, channel 0, and it's either going to be on or off depending on the analog value it receives. So if I remove this node and plug in my little analog node, so out of frame. All this is a little pot. It's actually a 10 turn pot, so it's quite a lot of turning. So it's wired, if you like, to this LED. So this is like a fuel tank on a car or something. So once the level of fuel goes below a certain limit, this light changes its status. Now I've obviously got these in reverse logic. You'd expect the light to come on, but I'm going to lower this, and hopefully if we get to a threshold, I shouldn't have used the 10 turn pot. There you go. So below a certain threshold, the master is, what this node actually does is it starts a timer. And where's the, so its initialization function just starts a 1 second timer. Again, its main function does nothing, or its loop processing does nothing. So on initialization, it just starts a 1 second timer that repeats. So repeat this timer and call this sample function. Every second it calls a sample function, and all the sample function does is call a low-level libsup code to take a sample of a particular I/O pin. And the way the code is structured, I haven't gone over ADC yet, but it passes because an ADC sample isn't synchronous, it's asynchronous. You don't know when it's going to finish. You pass in, as long as the pin you want to sample, you also pass in, this is the function I want to process the result. So at some point in time later, the result is passed to this of your analog sample. And all this code does is say, well, if the sample is different, if the last sample and the current sample are different, then send on an analog input status message. And every 1 second, if there's been a change in the data, it sends that on. And the analog, the master, it has a callback on that message, and it's just sending out the switch status saying on or off depending on that result, only to IO node 1. So if I was to reconnect the green LEDs, which are on node 2, the individual green LED wouldn't change. And that's all that's happening here. You've got a master which is processing messages. Which way am I going here? There you go. So every second it's receiving a message, and this master saying, yeah, send a status to that. And that's the project. None of these messages mean anything in terms of there's no fixed. I've kind of said that my can frames represent a data type, so one particular number represents a digital input in this. Now what this, and there's another can frame identifier that represents a digital output, a switch output, so these can be on or off. But the network doesn't have any information about what this represents. It doesn't need to know. That's internal to the logic of your master, which dictates the messages in response to other messages. So once it receives a message, it does whatever processing it wants. And that's the cinnamonBun open hardware, and the other two projects, libsup is the low level, and then the node management just makes it easier to write an application which just does call this function when you receive a status, an analog input. And that is pretty much the project. It's a work in progress. There's a lot of work to do. This is just showing the, if you will, the low level layer 2 messages that are passed about, but above that there's going to be ISO 15765, which is a layer 3 protocol, and that's going to manage the various nodes at a management level, none of which your application needs to worry about. Your application is just an input, an init function, and then your main, which is called from the loop, the main loop of the node. I hope that makes some sense. And thanks a million for watching. I'll get back to in the next video, I'll get back to actually going up the layers gradually, step by step, to demonstrate and show you what is the functionality. But yeah, that's the ultimate aim, is to get this into a vehicle, and you can change the functionality just by reflashing code into this. These nodes know nothing about the other nodes connected. They don't have to know anything about. It's the master that dictates the functionality of the network. So changing the master, and we can change whatever functionality we want. Once again, thanks for watching.